All right, are we going? Okay, I think we are. Great. All right, hi everybody, and welcome to our first official live class for Chem 100 this semester. Uh, Hope it works. We'll find out. So, hopefully you can see me, and those of you in the class, if you're watching, it's a couple things that can make this really useful, and this is what I've done before with other classes. Have the Discord up on a second screen, or you can just kind of switch back and forth if you're on like a phone or something, so that you can ask questions. One of the advantages of doing this in this particular format is that you can ask questions and I can respond to you right away instead of email or chat type stuff. So I'd be happy to answer your questions. I'm also going to, as I go through this, pause and ask you to answer some questions. We'll be following primarily this handout that I've posted on Blackboard that you can complete and submit, and we'll be going through it together. There's not a requirement to be here live or anything like that. I just want to make this available for people who like this sort of interaction. Um, and time wise, we have to find times that work well for all of us throughout the semester. For me, I'm most limited by my kids' e-school schedule. So, like it's after school now, so I have all the internet to myself. So this seems to be working okay, but I'd like to get some stuff earlier in the day also, or maybe in the evening or something like that. All right. So before we get started, are there any general questions that you want to put through to the chat here? Just again to the Discord. Oh, you're getting an error using the link. All right. Let me see if I can fix that. Sorry. Maybe it's here. I tried to make a direct link to this particular stream, but that didn't seem to work. So that should that should put you at least into the channel. By the way, we're in the live streams channel on Discord. So if you want to follow along and add your questions. All right, let's talk about the scientific method. So if you've done any sort of science before, you've probably heard about the scientific method. And we're going to or use as an example here the broken TV. So a couple of reasons for that. One, that's something that you maybe have experienced or something like it, and it shows that we use the scientific method all the time, even when we're not thinking about specifically doing science. So let's look at some of those features. So you go to use your TV, you hit the button, nothing. So nothing happens. All right. So what do you do? Well, first, you have to figure out what's causing the problem. Why isn't the TV turning on? So you're going to make a hypothesis. What's the first thing that you maybe think that, or the first reason that maybe you think it didn't turn on? So the example given here is an invisible fairy absorbed all the energy from the remote. I mean, that's possible, right? It could be. It's possible, but it's not really a hypothesis. And the reason it's not a hypothesis is because it's not testable. We might believe that a fairy sucked all the energy from the remote, but there's nothing we can do to find evidence to support that idea. And so as a useful hypothesis, it's not. It's not a useful hypothesis. That doesn't mean we're saying it's absolutely wrong. It just means that we can't test it, and therefore it's not a scientific way of looking at it. So maybe another hypothesis is the TV didn't turn on because the remote's batteries are dead. This now, batteries are dead, that is a testable hypothesis. We can take the batteries out, put new batteries in, or we can test the batteries, um, change the batteries, and what if the remote works? All of a sudden you hit the button and the TV turns on. Well, then that's evidence to support your hypothesis. So your hypothesis was, we're still not going to say it's totally right because we always have doubt when we talk about science, when we talk about knowledge. There's always some room for doubt there, but we have some good evidence that that's what it was. And of course, if it still doesn't work with new batteries, then we have to adjust the hypothesis, because if our hypothesis of batteries are dead was true, then putting new batteries in should have fixed that. And since it didn't, we can say, all right, well, there's some evidence that maybe that hypothesis is not actually correct. So we could do this over and over and over again, trying various different things, different hypotheses. Does anybody have a good idea in the chat? So if let's say our results disagreed, the remote still didn't work even after the new batteries. What would you try next? What would be another hypothesis? Could somebody send a testable hypothesis? No testable hypotheses. Looks like 3 people are watching this live. So if you have an idea for a testable hypothesis, go ahead and put that in. All right, so idea Alyssa says satellite is out. Yeah, so that might be the next thing, that maybe there's something else that prevents the TV from turning on if it's not connected properly. So then we could go look at those sorts of things. We could test that as well. We could go, do whatever we had to do to test the satellite um, and check it. Now that's the other nice part about that hypothesis, or the thing that makes it a little tricky, is what if we can't test the satellite? We don't have the equipment. We don't know. We don't have another TV or something to hook it up to. Well, in that case, we have a testable hypothesis. It's testable in theory, but we can't physically ourselves actually test it. And that's what happens in science a lot too. You can propose a testable hypothesis, even though we don't have the technology to actually test it yet. So things like atomic theory, when that was first proposed, there were various ways that there were various things that gave evidence to the fact that, or to the idea that matter was made up of atoms, but we couldn't actually test it at that time, and of course could then later. And Maria says TV is not hooked up properly. Yeah, not hooked on properly. So it could be unplugged or something else. The power could be out. There are various other things that we could propose as hypotheses. And then after we've tested all of that, we might come up with something we could call a law. A law has no explanation for like why something is happening. It's just stating some observations that tend to always happen. So, um, a TV will not turn on if it's unplugged. It will not turn on if the power is out. The TV will not turn on via the remote if the remote's batteries are dead. So, none of that really speaks to why the TV is turning on and off, or the TV isn't turning off, or why the remote's batteries have to work. But they just say, we saw that this happens and this always follows. This always causes this. This won't work if this. So that's what we call a law. And the theory then is the reasoning behind that. The highest level of scientific knowledge. Highest level meaning it's when we really understand what's going on, we have a theory. The TV will not turn on because there is no power source to supply the beam to trigger the infrared receiver and so on. So very specific instructions about how the remote actually works to turn the TV on. So the thing that's sometimes a little bit tricky about this is we often, because of our use of these words in non-scientific contexts, we often confuse the actual scientific meaning of these words. So a scientific law and a scientific theory are very different than a law in the legal sense and a theory in the idea sense. And this causes some really bad confusion because people think, oh, a theory is just some sort of idea. It's an unproven idea because that's what theory means, like in the non-scientific um, realm. Like, oh, I have an idea about something. That's a theory. And a law is like a concrete, you know, passed by the government enforced thing. So in non-scientific context, those mean very, very different things. Um, but in the scientific context, a law is just a set of observations that kind of always happen. And the theory is the reason behind those things. Why are those things happening? That's what we call the theory. And both of these have to be supported by evidence, and they can both be undermined by evidence to the contrary. So if you're doing experiments, if there's some well-regarded theory, but then you do a bunch more experiments and you realize, something's not right here. We have to adjust this theory. That's exactly what happened with laws of motion in physics. Newton's laws that talked about, if you throw a ball, how far does it go? Those are great laws, but they tended not to work in certain situations, like really small things, really fast things, um, really big things like planets and stuff. So they had to be adjusted with these ideas of relativity and quantum mechanical laws that would come later. All right, so let's try it. And again, if you can't see this text behind me very well on the screen, you can pull this down from Blackboard in the week 1 folder. So let's identify the steps with the first one, and then I'll let you do the other ones on your own. A person had a pound of fish and a pound of salted fish. 1 week later, the person saw that the salted fish was still good, but the unsalted fish had spoiled. So, what would you say is so that's the observation. What's a hypothesis? Anybody interested in trying a hypothesis for that first one? Salt prevents spoiling. Sure. Yeah. So that would be a good hypothesis. And that's pretty testable, right? We could salt things at different levels or different ways and try to figure that out. Another interesting thing about uh, this is something that, would have happened a really long time ago before the modern codified scientific method. And so this is just a way that people have been interacting with the world and trying to find out about their surroundings for a very, very long time. We call it the scientific method now. It consists of these specific named steps, but it's something that people have always done. All right. And there's some more examples there. I want to go down now to these last couple and show how we distinguish some of these things. So let's look at 3b here. The tides in Earth's oceans are caused mainly there we go. You couldn't see my pointer before. The tides in Earth's oceans are caused mainly by the gravitational attraction of the moon. So where does that fit into? Would that be an observation, a law, or a theory? And what's the key to determine that in this sentence? The tides in Earth's oceans are caused mainly by the gravitational attraction of the moon. Go ahead and drop it in the chat there. Theory. Yes, that is a theory. How did you know? Or anybody else? How did you know? All right, so it's specified mainly by the moon. Yeah, and the key right is right before that. Caused. Right? Theories discuss causation. Why is something happening? And so if the tides are caused by the attraction of the moon, that's a theory. Now, keep in mind, is that like controversial or anything? No, that's we know that. We would say we know that it's absolutely settled. Nobody's I mean, look, there's probably some people out on the internet there somewhere, but most people are not disagreeing with that statement. It's a theory because of what it speaks to, because it speaks to a cause, not because of how true it is. So it's important to keep those separate. All right, and then number 4, let's look at those 4 and say which one of these is a testable hypothesis. Roses are more beautiful than violets. A plant needs at least 5 hours of sunlight per day to grow. Ice cream is delicious. Humans will someday land on Mars. Hopefully that one's pretty straightforward, but it is B. A plant needs at least 5 hours of sunlight per day to grow. Now, we're not saying that's true. We're just saying that's testable. We can get some plants, we can give them 5 hours of sunlight, we can give them 4 hours of sunlight, we can give them as much or little sunlight as they need, as we want, and we can figure out if that's true or not. All these other ones are not testable because they involve preferences like more beautiful, delicious, or just things that, you know, are in the future that we can't test unless we had all time. Okay. All right. So now we're going to change a little bit. That was important to get some terminology straight. But now we're going to look at some units and some measurement. And you've probably, I'm sure, measured things in the past. You may have learned all of this stuff before. So, you know, if you have, that's totally fine. But if you have not, then it's time to learn this stuff. So we're going to focus on these 5 quantities for now. And then in lab this week, we're going to practice some of these measurements and doing them properly. In my experience, most people have experience with some measurements and have certainly measured things before. Most people have decent facility with the metric system, but the very specific way that we measure things in science and particularly with how it fits with the precision, that's what's a little bit different. So I'll probably spend a little bit more time on that part. All right. So for length in what we call the English or the imperial system, we've got inches, foots, miles, yards, all kinds of strangely associated units that are confusing if you haven't grown up with them. And what an example of an instrument to measure length would be, maybe a meter stick or something like that. Mass in the metric system is the gram. We often think of mass in the English system as the pound, but it's really not. It's actually this unit that I've never really used called the slug. Pounds are technically a force because they're a measure of a force that's put onto the ground or onto the earth. So the mass and weight differ if you're not on Earth. And that doesn't happen a whole lot, but slug is a measure of mass, which is the mass, the amount of matter that something contains. a very specific measurement, whereas weight is the force, the gravitational pull on that matter. Right? And so something we might use for that is a balance or a scale, and we'll be doing that on Wednesday and the Wednesday after. Okay, volume. Volume is how much space something takes up. In our English system, we might measure things in ounces, actually fluid ounces, because ounces are also used for weight. But cups, pints, quarts, gallons, and so forth. In the metric system, we're going to use the liter, which is capital L is its symbol. There are two correct spellings of liter, Liter, Litre. That's kind of like the French spelling. Either way is fine. We'll also, of course, use the prefixes, which we'll talk about in a little bit. To measure volume in the lab, we most commonly use a graduated cylinder, and I realize you can't see that behind my head, but I'll move it up a little bit there. Okay. All right, time, at least one thing stays the same, right? Time is the same in all systems, and we might measure that with a clock or a stopwatch or something like that. And temperature. Now, temperature is going to give us all kinds of trouble. Uh, so we'll talk in a little bit about the temperature scales and how to convert between different temperature units. Here in the US, we generally talk about degrees Fahrenheit on the Fahrenheit scale. And in the lab, we will generally use degrees Celsius. Kelvins is another measurement of temperature, but we generally only use that when talking about really cold things. We'll use it sometimes in this class, but not a whole lot. We'll generally stick to either Fahrenheit, which we know if we grew up in this country, and Celsius, which is more what we use in the lab. And of course, the measurement tool for that is a thermometer. All right, before we jump into the metric system, then, any questions about those in the chat here? All right, go ahead and jump in with your questions at any time. Just type them in, and I've got it up right here, so I'll keep checking and respond to you right away. Okay, let's look at the metric system. So, as you may have learned in the past, the metric system involves prefixes, parts of words at the beginning of the stick onto the beginning of a word to change the meaning, and these are going to be multiples of 10. If you grew up in a place that uses this regularly, you probably know most of these already. But if you grew up here in the US, you may not. So this is a good time to learn them. Specifically in this class, we're going to use these three, milli, centi, and kilo, along with the base unit. It's always useful to know these things, especially if going into medicine, because medicine is dispensed in all kinds of different quantities depending on what kind of thing it is and what you're doing. So you'll almost certainly come in contact with all of these prefixes at some point. But the nice thing, of course, about the metric system is not only the nice even numbers, but the prefixes are always the same no matter what you're measuring. So you can have, milligrams, centigrams, milliliters, centiliters, millimeters, centimeters, and it's always the same factor. So here are some common units of measurements that you can put in. I'll let you go through these, but how would you measure these things? In order to do this, you have to think about what is it you're measuring, what type of quantity, like we saw before. Are we looking at length? Are we looking at time? Are we looking at mass? Or are we looking at volume? And then what are some two common units that you could use for that? The other thing about this question is there's a question of scale. So if you're measuring the length of your textbook for the example here, which the example is given inches or centimeters, you're not going to use meters to describe the length of that textbook. I mean, you'd get a fraction of a meter. You're really certainly not going to use kilometers or kilometers because now you've really got a small fraction of that kilometer. So that's probably not a great choice either. You're going to want to use something that is um, approximate in size to whatever it is that you're measuring. If we look at these, so those are some factors, and you can answer some questions about that. Again, let me know if you have questions or if you're not clear. I'm not going to be grading this packet on that you got everything exactly right. We're using this packet to practice and to work through some of this information. And then my expectation is that by the time we get to the quizzes and especially the exams, that you then know these things. So we'll go through this packet mostly together, and there will be answers probably posted to some of the stuff after you've had a chance to look at them. And I expect you to ask me questions about it, and I'd be happy to tell you answers about it. But ultimately, it's the quizzes and the exams that we want that for. All right. So, making measurements, a couple terms that you will need to know: qualitative versus quantitative. So, qualitative and quantitative are shown here. Qualitative data, qualitative data, some examples are here. Quantitative, some examples are here. I want you to think about how you would define this for yourself rather than just giving you the definitions. I think you can probably figure that out. So if you're describing an oil painting, qualitative data would be maybe some colors, some smells, some textures. Quantitative data would be the sizes of different parts, the mass or the weight. So how would you describe those two different types of data? You can put that there, or you can drop it in the chat if you want me to check it for you. A couple more terms that we use in science in a way that we don't necessarily use the same in everyday life is precise and accurate. These terms are, I would say, pretty interchangeable when it comes to just everyday life. Precise, accurate, same thing. In measurement making in science, we have a specific definition of these in that they're separate from each other. Accurate has to do with proximity to the accepted or known or correct value. So, how close is your measurement to the real actual thing? Precision is about how repeatable is that measurement. So, if you do this thing several times, do these measurements agree with each other or not? So, if you're shooting at a target, kind of the classic example here, you could be accurate and precise, meaning you were close to the target, the spot of the target that you were aiming for, assuming you're aiming for the middle of the target. And you have a lot of precision because all of your hits are very close together, so you're able to do the same thing over and over again. If you have no accuracy or precision, they'll just be all over the place. Although in some cases you can still get an accurate value if your error is entirely random. So let's say you're shooting in such a way that you will always have a random error of some sort. If you make enough shots, eventually you'll be able to average things together and still get an accurate value, even though they were really kind of spread apart. Um, and then in the final example, you have something that is precise, meaning all of the things here are clustered together, but not accurate in that it's off center. So the types of I don't see that here. So let's talk about the wording here. If we're always off by a certain amount, get a different color. If we're always off here by a certain amount, then we can hopefully figure that out and correct for it. And this is what's known as systematic error. Sorry, my head's in the way again. Duck or something. Um, and if we just kind of are missing the target, but it's averaging out to the center eventually, then we have what's called random error. Random error can be nice because if you just do something, if you just make a measurement enough times, you can get rid of the random error because everything will average to the correct value. Systematic error is usually because something is wrong, like your instrument isn't calibrated right and it's always off by 2 or something like that. And these are things that we'll deal with more in the lab as we make our measurements as well. All right, so now we get to the part, and let's see how much room we've got on here. So about reading measurements. So I'm actually going to stop here for now. Um, this is the next part that I want to spend a little bit more time on. So I want to make sure we have enough time, and we'll do this for the next stream. I've scheduled the next one at this point. Actually, I don't remember. When did I schedule the next one? It's later this week, maybe Thursday night, I think, Thursday evening. So we'll revisit this then, and we'll talk a little bit more about how to make these measurements. Go ahead and work ahead if you'd like. Review this if you want to go back to some of the other stuff. The Mastering Chemistry, which should be live now, has some practice problems for you for this also. I've put those due dates, I've set them back a week just because of all the issues with getting Mastering Chemistry going at the beginning. But you should still start working on them now if you can get in because they apply to this week. All right. So as usual, let me know if you have any questions, and I'll see half of you in lab tomorrow, Wednesday, that is, and I'll see the other half of you the next week. But hopefully we can keep having good conversations online about all this stuff. So, bye.